Well, good afternoon, class. This is Mark Gastonguay. We're in our lab session today in MI210 on the topic of covariant modeling. On Tuesday, I'd reviewed some of the different strategies for covariant model building and some of the points to consider. And then this afternoon, we're going to review some of the practice problems on this topic. The first problem was more of a thought problem. It's nothing that you needed to do hands-on, but was really designed to get you thinking about how you might construct a covariant modeling plan, what strategy might you undertake, and what things would you look out for. So, for example, we started off with some information about the model, a population PK dataset, 300 subjects, 4 samples each. So what we're saying here is that there's a good amount of information, a decent number of subjects, 4 samples per subject in a pop PK dataset is not bad, depending upon the structure of the model. And the next bullet says it's a one-compartment model with large inter-individual variability. So one compartment model is pretty simple. 4 samples per subject for a one compartment model is probably quite informative, depending upon where those samples are located. The prior information indicates that there's also a significant drug-drug interaction identified in vitro with a commonly used combination. And so we're asking you to confirm presence in the current trial. And other covariates include weight, age, race, sex, liver function tests, creatinine clearance, and a couple of conmeds. So what I had done is to ask you to think about the steps you would undertake to build a covariant model, including the details such as the plots you might create, estimations methods used, covariant model building strategies, assumption checking, all of those issues that we've talked about in the past. And so, maybe I'll just share a few ideas with you now, and there's no right or wrong answer here. It's really just thinking about what you would want to plan. The first part of the problem here indicates that you've got large inter-individual variability, decent information within each individual. And so that's a hint towards making sure that you use an estimation method that's adequate, one that is a conditional estimation method, and I'd probably suggest using FOCE interaction as a starting point. Now the drug-drug interaction piece, so you have some prior knowledge there, and we have other covariate effects. And so if we're asked to confirm the drug interaction effect in this clinical trial, well, we want to first make sure that we have adequate inclusion of that drug interaction effect and a supporting design for the estimation of that effect. So ideally, we'd have a design where you have the same individuals with and without the interacting drug. That gives you a within individual comparison, which is much more powerful and reliable than a comparison between individuals in a more parallel type design. Most likely, you're going to have in just a typical trial POP-PK data set, you'll have some individuals on the drug and some who are not on the drug, and so it's not quite as reliable as your traditional drug-drug interaction clinical pharmacology study that might be done. The other covariates, again, you'd want to explore the range of the values. Make sure you have adequate range, liver function and creatinine clearance indicating renal function. Before we even undertake these, we want to make sure you have individuals with organ dysfunction and organ disease. Otherwise, they're essentially healthy with respect to those covariates, and it's not even worth looking at those. Of course, we'd want to do some data reduction by exploring the correlation between predictors and making sure to select unique identifiers, unique predictors of PK parameters for inclusion in the model simultaneously. You can obviously try different predictors in different models, but in the same model, we want to avoid the correlated predictors on a particular PK parameter. And then, depending upon your goals, if you're doing this for labeling purposes, you might want to do something more pre-specified, like a full model approach. If it's just a data mining exercise, exploratory, you might suggest a stepwise modeling approach. But since we do know this drug-drug interaction effect is something we're interested in, you want to make sure that that's included in the model. And then your usual model building process would proceed. Start with a base model without covariates, include the covariate effects of interest, and then use whatever method you'd like from there, exploring any remaining trends between random effects or weighted residuals and the parameter estimates, and then summarize the results descriptively. I don't think it's really necessary to have p-values because, as we said before, their reliability and accuracy is suspect. But what's really important is understanding the size of the covariate effects and the impact of those covariate effects on something you care about, like AUC or total or C steady state average or some response at a particular time. That's what makes most sense. So those are some ideas. Keep those in mind and maybe work through just that thought exercise on your own. It doesn't have to be for this particular problem, but take some real world problem that you might be faced with and sort of sketch that out and write yourself a brief modeling plan to support that strategy. Okay, problem 2 is the hands-on problem. And this is one where we're going to be building a population PK model with covariates. I've already created the data set for you, so I've taken that step away. It's a multiple dosing data set. This is a intermittent infusion, 3 hours of infusion given every 12 hours times 10 doses. And we've got each one of these infusions is a 900 milligram dose. And we've got multiple samples here, plus some troughs along the way. I've given you some initial estimates from a prior analysis or from some historical data. Clearance is 13 liters per hour and volume is 75 liters. So I want you to think about model building methods, goodness of fit criteria, build a covariate model, and define the impact of renal impairment on the clearance for the drug label. The data are included in a data set already constructed for you. So let's dig right into that and we'll take a look at the data. So I've loaded this up into the CIMI interface to our web server. Let's take a quick look at the data set. So we have the usual columns, comment column, ID, dependent variable, amount, interdose interval, ADDL, time, rate, and so on, plus some covariate effects, height, weight, creatinine clearance, sex, and age. We'll notice here that the amounts are on the dosing records are 900. Remember, it's a 900 milligram dose. The interval is every 12 hours. We have 9 additional doses. That's administered at time 0. And it's administered at a rate of 300 milligrams per hour. That gives us the 3-hour duration of that intermittent infusion. And then after that, we have the covariate factors for each individual. So your typical comma-separated file, this is something that you're all familiar with by now. I'm going to open up, I started an R script here, and I'll open that up and we'll do some exploring. So I'm working in a covariates subdirectory here. This is called covariates problem.r. You don't have this. I had given you just the data set this time to let you really start from scratch. but I will share all of these files and examples after this session today. Okay, so let me go back to the home page, and I'll fire up an R window as well. There's our R home, our R prompt, and we'll start off with the usual stuff, just cleaning up, loading the packages that we need, setting working directory and the NONMEM run command. This is standard code, at least while you're working in this course. You can use this almost verbatim. The only thing you need to change here is your working directory if you happen to use a different subdirectory name for the topic. And of course your username is going to be different than mine. So we'll evaluate that block and just double check. Okay, everything's done. The packages have been loaded. We've set our working directory, and now we're setting our NONMEM run command. Okay, so as we discussed before, the first thing before we do any modeling, we want to think about data reduction, and we also want to think about a plan. And so I'm going to take the approach here. We're going to try a full model approach. We could also investigate the process for conducting potentially a stepwise backward analysis. But we'll start with a full model approach. And so one of the things that I want to do is to think about what are the variables of interest. So we can read in the data set, but the data set, to just refresh your memory, includes things like height, weight, creatinine clearance, sex, and age. And one of the questions, the clinical questions, was, well, what's the impact of renal impairment on the clearance of this drug? So creatinine clearance is something we're interested in. The other things, height, weight, sex, and age, well, they're all, along for the ride here, and we could probably investigate those as well. But we're going to have to think carefully now about their inclusion in this model, especially if we want to include them simultaneously. So the first thing I want to do is import the data set and then do some exploratory graphics. So I'm going to read the table in to a data frame called data, make a few plots here. Okay. And then those plots we're just going to look at the dV versus time, and then the dV on a log scale versus time. And then to create some index plots. Index plots here, remember, are when we plot everything versus ID. Okay, that's finished. And we can go back here. We'll have to refresh. And here's our PDF file called Exploratory Graphs. All right, so we'll load this up. Now this is just a plot of the population data. You see the dV column here, or the observed concentration versus time. And you see the more extensive sampling of the first and last dose, plus some troughs in this multiple dosing design. And then the same thing here on a semi-log scale. These are useful just to look for the pattern of the data, any obvious outliers. Also, you can look at this decay phase here, and it's hard to tell. We don't have that many samples, but it doesn't appear to be any multi-exponential decay. So that's one thing we can learn from this. Then the real interesting thing is starting to look at index plots. And remember, the last time we used index plots to find errors in the data or problematic records. And so let's look for that again. When we're looking at the scatter matrix, the first place I look is at either the row or column associated with the ID. Let's look at the top row, where we have ID versus dependent variable, and there's a range of dependent variables here from 0 to 20 or so. Nothing really stands out there. We have an amount column. The amount looks like we have a bunch of zeros. The label's down here. And around 900, there's a bunch. Again, that's also expected. Zeros would be the PK observation records, and the 900s would be the dosing records. The next one here, we have interdose interval, and those are 0s and 12s. That makes sense. It's a 12-hour interval. ADDL, again, 0s for the PK sampling. And then we've got 9 here. Everybody's got the same number of doses, so that looks good. The time points are relatively consistent here across individuals. We have more dense sampling early on, some sparser trough sampling, a little more dense sampling in the last dose, and then that final point post-dosing. Same pattern for all individuals. And then when we look at infusion rate here, we see at 0 there's a cluster. Those are the rates on PK observation records. And then over here at 300, those are the rates on the dosing records. So these are all of the dosing control and observation time records. And they seem to be in order. There doesn't seem to be anything glaring there. Let's look now at something maybe a little more interesting. We're going to look at the covariate. And here we have, across the index plot, we have ID versus height, weight, creatinine clearance, sex, and age. And you see, a pretty decent scatter here. Nothing really unrealistic. The heights range from 40 to 110. This is centimeters. I'm sorry, probably inches. Not sure what we've got here. Anyway, we've got weights in kilograms, again from 40-ish to 100-something. Creatinine clearance now from below 50 up to this really high point around 200. It's probably unrealistic, but oftentimes you'll see that with calculated Cockcroft-Gall creatinine clearance. We have sex 0 and 1. These are just male-female categorical indicators. And then age range here from 38 to 50-something years of age. Nothing really outlying here. We've got one individual that's a little bit younger, but everybody seems to be within the same sort of cluster. So a few things we could learn here just from that first investigation. Number one, what sort of a range of values do we have? Well, we've got a decent range of height and weight. Creatinine clearance, we have a lot of points clustered here around 50, maybe between 50 and 100. And that's in your range of mild impairment to normal. And then a couple of these higher ones here. So there's something right away that we can learn from this, in that it doesn't appear that we've got a very broad range of renal function. Typically when we're looking at creatinine clearance in mils per minute, if we want to estimate renal impairment effects, we want to have individuals, in a category between 30 and 50, and then below 30 mils per minute to characterize the moderate and severe impairment. In this data set, that's not quite so clear. It looks mostly everybody's here is mild to normal. So just as part of the data reduction, we could limit our expectations on the investigation of the renal effects. In fact, if you were asked this by somebody in your development team, you could go back and tell them, say, well, gee, we're not going to be able to estimate impacts of moderate to severe renal impairment because we just don't have the range. We don't have the data. We can maybe estimate what's happening in the mild impairment to normal range. But it certainly isn't sufficient for anything like labeling or any inferences about moderate to severe. Similarly, we can look at age here and look at the range we've got in age, about 12-year span in our entire data set. So we've got a small range of ages, and probably not worthwhile to investigate into too much detail. Of course, this is a simulated data set here, and you know, some of the heights might not be so realistic for the age ranges we have, but you get the idea. So there's more that we can learn from this plot, and that's the relationships between the covariates themselves. Clearly, you can see strong relationships between height and weight and creatinine clearance, even differences in weight between males and females. Trends with age are quite small, and no strong correlation there. But really, you know, these 1, 2, 3, 4 covariates are highly correlated: height, weight, creatinine clearance, and sex. So we're going to have to think carefully about what to include in the model. And you know, this is a typical thing you're going to see with these types of covariates, especially when your range of renal function is relatively normal or mild. Most of that change in calculated Cockcroft-Gault creatinine clearance is due to body size and not necessarily impairment of kidney function. So we have some issues to think about here, and I want you to keep those in the back of your mind as we continue with the model building process. Now that we've looked at the data, let's go to a base model. So we want to create a control stream and run NONMEM. I've started off one here called 500. Let's pull that up. And this is very similar to the POP-PK models that we ran in the last session, except now we have covariate effects. I'm going to start off with a simple model, ADVAN1 trans 2. If you recall, ADVAN1 refers to a one-compartment model with IV input, and trans 2 is a parameterization in terms of clearance and volume. So we need to specify a PK block, which includes the required parameters clearance and volume. And if you're not sure about that, remember, just go look up the NONMEM help for ADVAN2. Sorry about that. ADVAN2. I'm sorry, ADVAN1 trans 2, which gives you clearance and volume estimates as your standard parameters. We've written them now as a fixed effect theta 1 and an exponential inter-individual random effect. And same thing with volume theta 2 and log normal eta 2. The scale parameter here, S1, represents the compartment that should be scaled so that we can convert the mass transfer in amount to concentration, which is our observation units. Other than that, that's all we need in the PK block. You know, the other optional items are a lag time, a bioavailability fraction, and so on. We're not going to estimate rate here. Rate is in the data set. It's a known infusion rate. So we're starting off with this basic PK parameterization. In the error block, we're going to define the way that the prediction is related to the observation. Here the data y are equal to the prediction f plus a proportional residual error and an additive residual error. This is a useful way to start. We are not sure what the residual pattern is going to be, but as we look at diagnostic plots, we'll learn more. Okay, theta, I told you that we knew from prior knowledge that clearance had an initial estimate of 13 and volume an initial estimate of 75. For omega, this is the inter-individual covariance matrix. We're going to specify a full block here since it's just 2 parameters. We'll assume about a 20% variance on clearance, a 20% variance on volume, and a smaller covariance term. Sigma we're going to model with assuming a 20% proportional residual error and a standard deviation of 1 for the additive term. This is just a guess. I'm not sure what those numbers are. And then for estimation, what are we going to do? Well, let's start off here, and I'm going to do what I always tell you to do in practice. We'll start off at max eval 0. We want to make predictions at our initial estimates. But if you'd like, we can use a conditional estimation method, method 1, interaction, that's FOCE interaction, just so that we can capture the individual estimates. So this is what I'd like us to run here. It's a max eval 0 run, FOCE interaction, a one compartment model with a block covariance matrix on the current data set. So we'll save that. And go back to the R script. And I've coded up a call to non-R here. That's the command that we use to run run NONMEM, excuse me, from R. The syntax is simple. It's just a run number. The command here we defined up above, which is the NONMEM run command. We're running on a grid here, so make sure you use grid true. Diagnostic plots true. And we're also going to define here the continuous covariates, the categorical covariates, our parameter list, and the list of etas. And that's just for plotting purposes. Okay, so we can define all of those. These are not required, but if you have them, we'll be able to create some diagnostic plots. So just highlight the call to NONMEM and evaluate that. So you see the job was submitted for compiling. That was completed without error. Now the execution is running, and that completed. And I'm just going to hit return there. Go back to the run. And here's the run directory for 500. The thing we always look at first is the list file. That's the output from NONMEM. This echoes back what we have asked NONMEM to do. We're getting, we're using first order conditional estimation with interaction. Now you notice there's no evaluation here because we're running max eval 0. But we have an estimate of the objective function. And the final parameter estimates are equal to the initial parameter estimates. So that's exactly what you would expect. What we really are interested in is our diagnostic plots, and the default naming convention, it just says diagnostic plot review 500 for run 500. Take a look at that. That's a PDF file. So what do we got here? Remember, this is a max eval 0 fit. We're running the estimation at the initial estimates. We see the population prediction here at the initial estimates. But we do see the individual estimates. Remember, this does run one step of the individual estimation. And you see an improved goodness of fit here at the individual level because of those individual etas that are being estimated. From the population fit, doesn't look too bad at the initial estimates, maybe some bias here at the low end. We do sort of recognize the increasing variability as you increase with concentration. So we've got a heteroscedastic variance in this case. Let's look at residuals and weighted residuals. Again, you see some bias here, but remember we haven't optimized the parameters yet. So the fit's not perfect, but we get this hint of the proportional nature of the variability. Higher variability at the high end than the low end. So that's our diagnostic, that we do need that proportional component in the residual error. On the weighted residual, it does seem to balance the data a little bit better, but we're going to have to estimate the parameters to confirm that. When we look at things versus time, you do see the runs and residuals here, but remember, this is max eval 0, we haven't optimized yet. We look at the QQ plots of the residuals. These should be normal. There's a little bit of skewness here for both the residuals and weighted residuals. Hopefully that'll be resolved. And again, just reviewing the scatter plots of the covariate effects. Plus some additional stuff here, but we're not going to look at this until we run the model. So let's skip these plots now. What we need to do is go back and run the model. So let's go back to 500. And, oops, that's not what I meant to edit. 500. In the interest of time here, I'm not going to rename this. I'm just going to keep the same run, but you would probably want to rename every run and keep a track of it. I'm just going to give us max eval 9,999. All the initial estimates look good, so we'll save that and go back to the R script. So I'm just going to put a note here, you know, first ran with max eval equals 0, then ran full estimation. So let's save that. We'll run non-R again. Same model run. Evaluate. And so compiling and now executing. Done yet? Okay, that's completed. So let's look at model 500. We'll look at the list file again. Here's our base model. And now we have some iterations to monitor. You see the parameters are scaled to 0.1. That's always the case. The gradients now start off at values like 10 to the second, 10 to the first, so pretty large gradients. And you see this gradient decreasing over time. We end up here though, look at the last couple iterations, I see something that's problematic. This gradient down here is 0 at the 20th and then the 24th. So that's the last parameter we're estimating, and that happens to be the additive term in our residual variance model. So that's telling us something about the residual structure. What else is happening here? Minimization was successful, but a parameter is near boundary. It's probably that last parameter. The eta bar, mean of the etas is quite small. P-values are large here, so it looks like our etas are centered well. Shrinkage percentage here, 1% and 5% for etas and 6% for epsilons. That's very small. So the individual data are influencing the individual estimates. Parameter estimates turn out to be about 11.8 and 85.6 for clearance and volume. We've got variance and covariance estimates here. But here's our problematic point. We have epsilon 2, or the variance of epsilon 2, being estimated at 10 to the minus 4th. This is the zero gradient parameter and the one that's causing trouble. So we'll have to remove that one to improve this model. Let's do that. So go back to 500. And let's save this now as 501. Base model without additive residual error. And how are we going to fix that? Well, we can just come down here and set this value to 0 and fix it. Or we could just eliminate epsilon 2 from the model. Just delete this and delete this. Let's do it that way. Okay, so let's update our run numbers. And let's try to run the covariance step this time. And we'll save this as 501. Close that. Let's go back to our script. Just going to copy and paste, and we'll call this 501, and we'll say removed additive residual error component. Okay, save this. All right, let's run 501 now. Oh, didn't like that. Let's make sure we have it. It's possible that I saved it in the wrong place here, so let me take another look. Yeah, here it is. So let's move this file. Or in fact, we'll just rename it. And we're going to save it. See, we're in this run directory 500, excuse me. So I'm just going to put the // we'll save it up one level. Okay, let's go back, refresh this, and there it is now, 501. So let's run our NONMEM again. Okay, we'll walk through this again. That seems to have worked. And now we don't need to create the exploratory graphics. Let's just run non-R. And the job has been submitted. And completed. Okay, well, apologies for the technical glitches there. If that happens to you when you're running this, just close the session and refire it up. We have a new version of this tool that will be rolled out for our next course. So again, apologies for that. But let's get back to the point of the analysis here. We just ran that 501 model. Let's refresh. Now we have 501. Let's look at the list file. And now we see a better picture. We see the gradients from large values going to smaller values, no zero gradients, no flip-flopping of gradients. Minimization is successful. Again, non-significant p-value on the eta bar, indicating the etas are centered at 0. Eta shrinkage is small, so we have reliable estimates of the individual etas. At least that's our estimate of the shrinkage. 11.8 and 85 clearance and volume, very similar estimates for the variance terms, and just a residual variance here of about 0.04, about 20%. That all looks good. And then we even get standard errors now because we ran the covariant step. Theta 1 here is 0.4 on the scale of 11, so it's quite small, 5% or so. 3.5 on theta 2, and that's got a scale of 85. So again, very, very precise here. All of these estimates are quite good, and that's because this is simulated data. But typically, if you see something on fixed effects parameters in the neighborhood of 10%, that's very good and attainable in some of the models. Random variance terms are usually less precisely estimated. Okay, so that's the base model. Let's go back and look now at some plots. So we ran diagnostic plots 501. These look better, don't they? So we see this cone-shaped relationship in the population pred-DV plot, or DV-pred. And that's still evident in the individuals, but of course a bit tighter because the individual random effects have been estimated. Residuals show you the same proportional shape, although the weighted residuals have sort of pulled that in. Looks like a few high values in weighted residuals here, 5 and 10, and these are actually conditional weighted residuals calculated assuming the FOCE interaction estimation method. So this is unusual to see large weighted residuals like this, but remember, we have not yet looked at covariate effects. Residuals, weighted residuals again. Here's our scatter plot. So remember, we said we wanted to investigate different effects. We know our age range is small, but we might want to estimate what we can learn from that. Creatinine clearance we know is limited, but as long as we limit our inferences to the range studied here, we're probably okay. Height and weight are highly correlated. So we're going to have to think carefully about how to construct this model. And so, one thing that I would suggest is maybe we look at creatinine clearance as a predictor of clearance, and then weight and potentially age too. Although you typically see a correlation there, but remember we don't have anybody that's very old here. Creatinine clearance age relationship is small, so we can look at creatinine clearance and age as predictors of clearance, and we might think about looking at age and weight as predictors of volume. Who really cares about height? In this case, it might be useful if you wanted to calculate ideal body weight, but that's not our goal right here. So that's one way to propose it. If we look here at relationships, we see that height and sex are highly correlated. So is weight and sex, although age and sex are not. So really, it's going to be difficult to include sex in this model because of it's correlated with two of the predictors that we're going to include. One of them weight on volume, and the other one creatinine clearance on clearance. The correlation between ETAs is not very strong, maybe a little bit, but that's good to know, because if it was a very strong correlation at this point in time, you might view that as an indicator of unidentifiability, non-identifiability of those random effects. Here's the histograms, roughly centered at 0, not quite so normal, but it's a small data set. And there's a density plot of the ETAs. Now here's box plots of ETAs by the categorical covariate, and you see that there's definitely a trend here in the random effects for both clearance and volume with respect to sex, where females slightly lower in both cases. And that's probably because of the weight dependence. And now here's some exploratory plots. We're looking at the effects of height, weight, creatinine clearance, and age on ETA1. This is the random effect for clearance. And, slight trends here. Creatinine clearance shows us something, not so much with age. But remember, we wanted to quantify the creatinine clearance effect and the age effect. So we'll move forward with those. Although you could probably argue that it's not worth looking at age because the range is so small. With respect to ETA2, this is the volume random effect. You see the height-weight relationship, creatinine clearance, of course, because it's correlated. Not so much going on with age. And this is where that screening comes along. You might not even look at age effects here because there's no relationship and the range is so small. But let's just keep these in mind as sort of like before and after comparisons. Okay. So now we need to build a full covariate model, and I've done that for you in something called 510. 510.ctl is a full model, and what I've done is constructed this using multiplicative power models. We have theta1, which is the typical effect for the reference creatinine clearance and the reference age. So we're using a reference creatinine clearance of 80, just along that cusp of normal renal function, and the reference age of 45 years. That was about in the middle of our distribution. We're raising theta 3 and theta 4 as the exponents here in this power model. In Fortran, recall that the operator for a power is a double asterisk. Same thing with volume. We're going to look at the effect of weight and age on volume. Okay. The rest of the code is the same. It's just that we need to specify initial estimates now. And we need to specify initial estimates for the covariate effects. Well, when you have a power model like this, sometimes it's nice to put the covariate effect at a starting point that's near its null value. Remember, theta 1 now is going to be a typical effect balanced at the typical creatinine clearance, or the midpoint of creatinine clearance and the midpoint of age. So what we want to know is, how much do these covariate effects pull away from that typical value? And that's where we can add a covariate effect like this power model at a value that's close to the null. So the null value here for theta 3 and theta 4 is 0. Now we can't start an initial estimate at 0, but we can use a very small number, and that's what we're doing here. There's no bound necessary because clearance will be constrained to be positive as long as theta 1 is positive. Theta 3 could be negative or positive, it doesn't matter. So we're not going to put any bounds on the estimation, and we'll do the same thing for age, weight, and age, again, on volume. And we'll run the same model. Here I've got the last sigma fixed to 0. We can just delete it as well like we did the last time. Either way would work. And we'll run the covariance step and diagnostic plots. Okay, so we'll save that. Come back to the R script that we're working on. So now we're going to run a full covariate model. And this is 510. All the same covariates are there. Save that. And evaluate. That's been submitted. So what we're going to look for now is the usual with respect to estimation of parameters, but in diagnostic plots we're going to look to see if that relationship that we saw between eta and weight, or eta and creatinine clearance, if that disappears. And then given that information, we're going to try to describe the effects of those covariates. So complete here, and we'll go back to the home page. 510 is our model. Let's look at the list file. And make this a little bit smaller. So what do we see in the gradients here? Positive values. It took a few more iterations because we're estimating more parameters. But in general, these seem to be pretty well behaved. No zero gradients. Minimization was successful. We've got a decent eta bar. Again, non-significant. Shrinkage is small. And now we have estimates for the parameters. So this is the power effect for creatinine clearance. This is the power effect for age on clearance. This is the power effect for weight, and the power effect for age on volume. Looks like age has a small negative effect. We also have standard errors of those estimates too, which we could compare. You'll notice that some of these are poorly estimated. So for example, the age effect, 0.7 is the standard error on a point estimate of 0.4. And that's not surprising because we have such a small range of ages. That's the age on volume. When we look at the weight on volume, that's got a standard error of 0.1 on an estimate of 0.4, so about a 25% error. On the effect of weight on, the age on clearance, that's a 0.49 on an estimate here that's 0.51, so a very large standard error, again indicating that we don't know much about age. We could probably guess that given the range that we have. and then 0.09 on the creatinine clearance effect, which comes out of 0.2. So that's to get better precision, and relative standard error there is pretty good. Okay, so we can learn a few things there. Let's go to the plots. Goodness of fit now even improved a bit more than what we had seen before, especially at the individual level, but even the population level, we see more of a balance around the 0 line. Residuals look pretty good here, no real trends. We still have a couple of large positive weighted residuals here at the very low predictions. Not really sure what that's indicating. It's these particular residuals here, and it might just be some additive noise in there that that's not being weighted very well, because remember we've removed that additive term. It's not something I would worry too much about, though. We look at them versus time. Looks pretty good. You just got a couple of late time points here with large weighted residuals, indicating an underprediction. Pretty well balanced, close to a normal QQ plot for both of these. Again, the tail at the extremes here. These are the scatter plots. We've already seen those. We'll skip that. Let's look at the relationships now between the random effects. And you remember we had a little bit of a trend before. Well, that trend is disappearing now, in that the etas are almost independent. And that's because we've explained some of the variability. Histograms of the etas look decent here. A little bit skewed on eta 2. Remember, we have a small sample size. Density plots look good. And now look at the eta versus covariates. So remember, eta versus sex, we saw the relationship last time. Now that relationship is gone. We didn't include sex in the model, but that's because we've included other covariates that were correlated with sex. And so we see no remaining trends there. When we look at the effects of height, weight, creatinine clearance, and age, we see no remaining trends there on eta 1. That's the clearance random effect. And then with respect to volume, again, no real strong relationships left there. Remember, this is a small data set just for the simple use of illustration in this class. So we're not going to we're not going to see too much in these trends. And any little deviation you see here at the tails, it's probably just because of small sample size. So this is not bad. We've got some improvement in goodness of fit. We've had a small reduction in the residual random effect and the inter-individual random effect estimates, and improvement in the overall goodness of fit. The last thing you might do is then try to pull these in and make some inferences. And so here's a technique you could use. There's a file that NONMEM 7 exports called the ext file, and the ext file contains the parameter search results through the iterations. What I'm going to do here is just read that in and pull the last row out of that file. Let me evaluate that. And then we could even, just display what that looks like. And here's what we get. We have now a small table that has the iteration number, the different theta estimates, omega estimates, and sigma estimates, and the objective function. You could use that then to calculate particular effects of covariates. So, for example, let's go back to the script. We could say, let's look at the effect of 50 mil per minute creatinine clearance on clearance. Well, for that we would just take the theta 1 value is already the typical centered value. Let's see how much less the the clearance would be at a creatinine clearance of 50. So one thing you do, you get to go final pars, and we could say dollar theta, and now I just know that it's theta. Actually, I better look again at the code. Theta 3 is our creatinine clearance effect, centered at a value of 80. So we can say theta 3, actually, we'll say 50 mils per minute divided by the reference point of 80 raised to the power of theta 3. And let's say we wanted to look at the other extreme, what happens at 100 mils per minute. So this is the fractional change. Let's execute these pieces. So in this case here, our estimate of the creatinine clearance effect gives us an effect of 0.95 for somebody at 50 mils per minute. So this is relative to the typical individual. You get about a 5% drop here. And relative to the typical individual, you get about a 2% increase at 100. So this is showing us here there's no real impact of the creatinine clearance. And that's because we got a small range. We weren't really able to estimate. So if we want to answer our question that we originally posed, what's the impact of impaired renal function? The answer is that, well, we really can't estimate an effect here. The point estimates lead us to very minimal change, but that's because we have a very narrow range of renal function. You do want to go back and study a population with more of a breadth of renal function. Okay, I'm going to save that, and I'll take a few minutes to answer questions now. So one question is, if you were in the situation where the base model didn't converge and the model with covariates does, would you feel comfortable? What would be the strategy to gain confidence in this model? Yeah, I think that's possible. I think that's a reasonable thing to do. And the particular case is when you have a covariate that is so strongly influencing the PK that if you don't include it, your model is just so completely misspecified that it won't converge. And an example I can think of this is body size when you're modeling a combination of pediatric and adult data. Sometimes that model is very unstable until you adjust for body size. So in some cases, I would agree that is a reasonable thing to do. I would still feel comfortable with the model if it's stable after adding the covariates. On the other hand, you also want to determine, well, why is the model unstable? Is your base model so over-parameterized that when you get to the covariate model, you have no chance of having a stable model, and that's a different situation. So be careful with that. But if you get to a stable model by adding the covariates, if the covariates are well estimated, you get back to those same estimates after trying different sets of initials, and you have a well-defined minimum. I think in that case, I would feel comfortable with that covariate model, even if the base model did not converge. Flip-flop gradients in the last parameter. Well, I'm not sure which one we were talking about there, but I think we did discuss how to deal with that flip-flop gradient. Why pick a power instead of a proportional model for the covariate effects? I just like the power model. I think it's stable. It always constrains the covariate effect to be positive. I'm sorry, it constrains the PK parameter to be positive. And it's a very flexible form. The proportional relationship, it's really an additive proportion, and sometimes that can flip to negative space in my experience, is not always as it's not always as stable. But you could certainly try a power model, proportional model, if you'd like. Next question is, when do we consider weighted residuals to be large? Weighted residuals greater than 3? Question mark. Well, there are different schools of thoughts here. I think, if you have weighted residuals that are greater than an absolute value of 5, you've got potential problems, and you might want to go back and investigate those points. However, if you have no reason for excluding them, you might try the sensitivity analysis where you remove the points, run the model, estimate parameter estimates, and then compare that to the same estimates with the large weighted residuals included. If there's no real change there, I would just leave them in the model. If you can explain why there might be some problems there, data errors or unrealistic data records, you might remove them. Given the data, is there anything that might hint to a better model? Thanks, Francois, for clarifying. Given the data, it's not completely obvious if a proportional model would be better than a power model. In fact, most of the time, we just don't have enough information about the individual covariant relationships to really discern those sorts of things. You might look at the relationship of the eta versus the parameter, or the absolute value of the eta versus the parameter of that absolute value of the eta versus the covariate. Excuse me. If that absolute value has sort of a proportionally increasing relationship, that might indicate that you need a proportional effect. But usually, we don't have the information to discern that, and I'd focus more on just a stable model. So the question is, what happens if we did stepwise backward? Well, you can try stepwise backward from this. You've got a nice stable full model here, and so what you could do from this is continue from model 510 and eliminate one covariate effect at a time, record the objective function change, and continue on. What's going to happen here is that I anticipate that most of these effects are going to drop out of the model as non-significant, except for the creatinine clearance effect, and maybe the weight effect on volume. So probably creatinine clearance and weight on volume. But the age effect, as we already saw, the confidence interval is very poor on that. It's going to drop out. But try it. Try it on your own. Okay, well, that brings us to the end of the session today. I just want to point out I suggested a few study guide questions. I don't think we need to run through these, but look back at your notes and make sure you understand these themes. These will be important for the exam, and these are the key points I want to get across in this particular topic. So lots more you could do here with these models. You could run stepwise. You could create some additional graphics. But this is the basic idea. And I'd like you to give it a try if you haven't done it already. I'm going to post all of this immediately after we finish class here, so you'll have the example scripts to play with. Any more questions? Okay, looks good. Then we'll end for today. We've got a holiday weekend coming up here, so we'll enjoy the weekend, everybody, and we'll pick up again next Tuesday. I believe our next topic is simulation, which is a very useful topic in PopPK. We'll talk then. Thanks a lot.